Alright, good day everyone. My name is Nikeshnan, and today I'll be talking about the Fluid Mechanics Lab 2, which is under Fluid Dynamics. And the experiment we're going to be discussing today is the Bernoulli's equation demonstration. Now let's begin. So a little bit of an introduction towards this experiment and the flow of fluid. So a flow of fluid has to conform with a number of scientific principles, in particular the conservation of mass and the conservation of energy. So the first of these principles is when applied to a liquid flowing through a conduit, requires that for steady flow, the velocity will be inversely proportional to the flow area. The second principle requires that if the velocity increases, then the pressure must then decrease. In order to apply Bernoulli's theorem, we have to assume three things about the fluid, which is the flow of the fluid is frictionless, steady, and incompressible. So the objective of the experiment is to investigate the validity of Bernoulli's equation when it is applied to a steady flow of water through a tapered duct. So the equation we're going to verify is the one on the right here, as you can see. Now moving on to methodology. So in this experiment, the validity of Bernoulli's equation will be verified with the use of a tapered duct or a venturi system connected with a few manometers to measure the pressure head and total head at known points along the flow. Now there are a few steps in this experiment. So the first step in the procedure is to place the venturi meter on a horizontal surface and note the height of input valve and output valve and make sure they are both the same. From there, attach the apparatus with the power supply, but keep the supply off and open all the air bleed valves of the manometer present at the top. The second step is to turn on the power supply to run the pump and adjust the flow rate control valve until water level is in all the manometers is at a readable range. Then place a stop plug in the basin and note the time required to fill the basin with a specific amount of water. Third step is to remove the stop plug to drain out all the water. Then place the dynamic pressure probe with the static pressure pot and measure the manometer data from both of the probes. Finally, the fourth step is to place the dynamic pressure probe next to the static pressure probe and measure the manometer data from the probes. Repeat the above steps for measuring data from all the manometer probes. Now these are the results and the discussion of the experiment. From the table here, we can note that the flow rate and total velocity was calculated using the Bernoulli's equation. And based on the results, the velocity of fluid is increased when it is flowing from a wider to a narrower tube as the pressure is lower at constrictions, and the pressure then increases as the cross-sectional area increases. So based on the table, we've plotted a graph on it, and based on the graph, you can see that the decrease in area of flow decreases the height of water in the manometer column. So what this means is that they are directly proportional to each other. And finally, moving on to the conclusion. So from the experiment that we have conducted, we have successfully demonstrated an experiment on Bernoulli's theorem. And based on this experiment, we can see that the different cross-sectional areas will give different pressure and different velocity, thus changing the flow rates on each of the segment. So when a velocity of fluid increases, the cross-sectional area decreases. So this experiment can be said to be the most suitable to be used to verify the Bernoulli's theorem, as the theoretical value and the experimental value calculated is not much different, not much error in both of these calculations. That is all. Thank you for listening.